Okay, hello. My name is Katja Niemann. I'm from the Fraunhofer Institute in Germany. We are a non-profit research institute and we are related to a university. And today I will talk about the clustering of learning objects. And I do so by only considering the usage of the learning objects and not as traditionally by looking at the content, because often we do not have any content. Often we have pictures or we have texts that are in different languages, and then it's really hard to cluster the objects or to find semantic similarities between them. And I will first give you an overview about the background in corpus linguistics, because I'm a computational linguist, and we have a lot of techniques to find semantic similarities between words that are used, for example, to create dictionaries. And we try this technique to cluster learning objects. And after that, I will present you the evaluation on 2 big data sets. So this is a graph of terms that occur often in learning analytics literature. It's totally made up, but it could be like this. And if 2 terms are connected, that means that they often co-occur together, for example, in a paper. So you see learning analytics and self-reflection significantly often co-occur together, as well as learning analytics and semantic web. So these are the first order co-occurrences of learning objects, of learning analytics. And we can also go one step further and say, okay, we are interested in higher order co-occurrences. We are interested in the next step in the second order co-occurrences. The second order co-occurrences of the term learning analytics would be ontology and RDF, for example, because I can go there in 2 steps using semantic web. And all the nodes from the right cluster are second order co-occurrences as well, because I can also go there in 2 steps. For example, from learning analytics to usage data, I can go via LMS or self-reflection or teacher support. Semantic web is really not a second order co-occurrence because there's no way to go there in 2 steps. I could go there in 3 steps if I go to ontology and back, for example, but not in 2 steps. And this way I can calculate third order co-occurrences, fourth order co-occurrences, and so on. We do not consider all co-occurrences. They need to be significant. What does that mean? So I can say 2 words are significant co-occurrences if they really often co-occur together. But the frequency alone is not sufficient, because terms that often occur are also expected to often occur together. So we need another significant measure. And for words, most often Poisson distributed significant measure is used. So what happens with these higher order co-occurrences? After a while, the clusters of higher order co-occurrences you get stable. They don't change anymore. So the 5th order co-occurrences, the 6th order co-occurrences, and so on are the same clusters. And they tend to be semantically homogeneous. So, and I have here, this is not made up, this is a real-world example. For the reference word IBM, and it's from the Brown corpus, it's a very common corpus in Germany. I translated the terms. And so I calculated, not me, but we calculated the words, the first order co-occurrences for IBM. And you can see this is computer company, computer producer, stock market, and so on. So terms that we would expect to co-occur with IBM. And after the 10th iteration, we get a totally new cluster containing the words Compaq, Microsoft, NEC, Cisco, Sony, and so on. And these are all the names of computer companies. So we really have a semantically homogeneous cluster. The same can we do for telephone. So the first order co-occurrences for telephone are mobile phone, frequently, email, corner, bell, internet. And here, after the 5th iteration, the clusters get stable. And you don't know that, most probably, but Backnang, Weiblingen, Esslingen, and so on are names of small cities in the south of Germany. So here we have as well a semantically homogeneous cluster. It is not related to the reference word, but it is semantically homogeneous. So in my research question, the question of this paper is if we can use this to also create clusters of learning objects that are semantically homogeneous. So in learning objects, for learning objects, we don't have sentences as we had before for words or documents, but we have sessions. So in this case, we have two users, and they both log in, for example, in a learning management system or in another platform where they can search for learning content. And they click on different documents, or they tag documents, they share them, and so on. And we can see, okay, they clicked on all these objects, and then they logged out. So here I have a context for a learning object that is similar to the context of a word in a sentence. And I can say, for example, okay, yeah, you can see it. You can take only the document that occurred right before, in this example, the picture, or right after the picture as content, as context. You can also take the whole session into account, and this is what we did. So in this way, you can create a graph of the learning objects as we did before with the words. And we calculated higher order co-occurrences of the documents and tested if they are semantically homogeneous. So we did this for two data sets. The first data set is collected in the MACE portal. MACE means metadata for architectural contents in Europe. It was an EU-funded project. And it enables students to search in different repositories in a unified way, just using this one web page. And they can tag the resources, they can share them, and so on. And we also have for all the objects, and this is what we used for the evaluation, semantic metadata. So we only considered learning objects for which we have at least an English title and an English description. So we could compare them using cosine similarity. And as I said before, we collect the usage data. So each event that a user conducts in this portal is logged. And for my analytics, I used if they go directly to a learning object, or if they have a look at the metadata of a learning object, or if they add a tag or a comment or a rating. So I use every event in which a learning object is involved. And I could use about 46,000 learning events that were collected in about 2,500 sessions. And this way, I could cluster about 3,700 learning objects. Oops. So this is about the distribution of the cluster sizes. And as you can see, the clusters are really small. So 86 of the clusters do contain not more than 10 learning objects, and most clusters do not contain more than 30 learning objects. And it's important to mention that this is not a hard clustering, it's a fuzzy clustering. So a learning object can contain to more than one cluster. And, but you see that most learning objects do not contain to more than 3 clusters. And this is how a real cluster that we had can look like. And this is a cluster containing 23 learning objects. And I show here the tags for the learning objects. And all of these objects were tagged with the tag ecological. And 10 were tagged with solar heat and heat recovery. So you can see this cluster contains learning objects that deal with eco-friendly living. And other examples are, for example, that we have clusters containing only Spanish documents describing material, mainly concretes and bricks. And that was very fascinating that we really had clusters that were all in Spanish or all in English or all in French. There was no mixing of the languages, almost no. So we did several statistical tests. I present you here the test for student t-distribution, which tests if the cluster means of semantic relatedness, which we calculated using the title and the description and the tags and the comments, differs significantly from the overall mean of the population. And it's a two-sided t-distribution test, and as you can see is that 80% from the 184 clusters are significantly semantically dense, and only 0.5% is worse. The other testbed is TravelWell. This is also a European funded project. This is not our project, but they made the usage data openly accessible. But yeah, we do not have as many event types as we had for the MACE project. The only event that we have is add tag and add rating, which is okay, but you only add a tag once, and you only add a rating once to a learning object, while you can often go to a learning resource and have a look at it. And we could use here about 14,000 events. We did not have timestamps, so we had a date. So we could say, okay, these events happened on one day, but we could not say in which order. And this is why we don't have a clear session definition here, but everything that happens on a day is in one session. And you can see here in MACE, we had an average session length of about 11 learning objects, and here we have a length of 55. And this results in much bigger clusters. As you can see here, 16 clusters contain between 101 and 125 learning objects, and there are even bigger clusters. And also, most learning objects contain to at least 7 clusters, which is also not so good. So we like the approach that we have a fuzzy clustering, but I think it is way too much if a learning object belongs to so many clusters. So here we can see an example cluster as well. In the TravelWell learning data set, we have learning objects that deal with education in school. And you can see here that this is a cluster containing learning objects about teaching English. It's with animals, it's for beginners, it should be fun to engage the pupils. And I also have another example, and this is something that happens quite often. They also have a basic computer science course in the school, so you see here hardware, software, so that they get a basic understanding out of it. But in this cluster, we basically have 2 clusters that are not separated, because we also have tags for continental drift, for example, or climate. And this is something that really happens often in TravelWell, and I think this is because we do not have a clear session definition. However, the test for student t-distribution is significantly good, because even if we have 2 clusters together, they are still more semantically dense as the overall population. Okay. This is my conclusion. So what is very good is, I was very fast, I think. What we found is that we could find semantic relations between objects based on the usage, and this is very promising, we think, for the future, because we would like to use this to combine with traditional clustering. So if you have metadata, great, use it. If you don't have metadata, use the usage data, because sometimes you can have it as well. We really need to investigate further in the significant measure, because we used the measure that that was also used for words, but maybe for learning objects we should use another measure. The session definition is not clear, so log in, log out would be the best, I think. We did not test the frames yet, and the day did not work. And we really would like to transfer it to other domains and use it in real time to also make recommendations. Okay, that's it.
Okay, we're doing very well on time, so we have plenty of space for questions. Anyone?
I wanted to make sure I understood your definition of coincident objects. When you say that they're 2 levels apart, you're saying you're looking for things that are 2 links away from something 2 links away from this object. Is that correct? Second order co-occurrences?
So for the second order co-occurrences, I was asked about the definition. Okay.
Repeat the question.
Okay.
Sorry, apparently I can't project as well as I think I can. So my question was, I was looking for the clarification of the definition of a second order co-occurrence. Is that something that's 2 links away from
Yes.
things that are 2 links away from this object?
Yes.
And third order is 3 links away from 3 links away.
Exactly. So for example, learning analytics and semantic web is also 3 links away because I can go to semantic web, to ontology, and back to semantic web.
Okay. My second question was, you state that you did a hypothesis test and you found that the clusters were more semantically related than just random clusters.
Yes.
How did you get that semantic scoring?
We are in the lucky situation that we have a learning object metadata instance for each learning object. And we only considered the learning objects where we had English titles and English descriptions, and sometimes we also had tags. And we used this to create a vector and calculated the cosine similarity.
Thank you.
Any more questions?
I'm curious as to why you used fuzzy clustering, which lets objects be in multiple clusters as opposed to just like a hierarchical clustering or something like that. Can you just comment on that choice?
Yes. This is because we found it very fascinating that this higher order co-occurrence approach does work on words, and it does for years. It is really used a lot to create dictionaries, and we just wanted to test this approach on learning objects, and it is by definition a fuzzy clustering.
Any more questions?
Yeah, I want to ask you if you see any application of this in a more learning-related context. Like, for example, I'm thinking about 2 possible scenarios, like instructors searching for relevant material for courses, or students also encountering relevant materials which would maybe similar to this cluster. Can you comment on that?
Yeah, this is absolutely the goal. So we want to use that for recommendations, so that we can say, for example, to students, okay, you had a look at this learning object and at this other learning object, so I guess your context is this. And then we want to recommend similar learning objects. And this is also something we can do for the teacher. If we know if he's preparing a course, he has a pretty great context that we can use for that.